So we should just get up the slide deck for Dr. Sugai LIANG. And
okay.
there you are,
Hi,
Sugai.
Everyone.
If you could...
It's my pleasure to be here.
Yeah.
The topic today is about the machine learning in neuroimaging of schizophrenia. And I'm Sugai Liang. I'm a resident doctor of psychiatry, and I work in West China Hospital, Sichuan University. And next. Yeah. So the machine learning is a set of methods that can automatically detect patterns in data, and they use uncovered patterns to predict future data or to perform other kinds of decision making under uncertainty. So yeah, I would like to point out the advantage of advantage about the machine learning. Yeah, it makes a group level comparison to the individual level. We could use machine learning to analyze several kinds of data, like the image, numeric data, or the text data. Next. Next, thank you. Yeah. Using the machine learning, we could do the analysis including classification and regression, clustering, dimensionality reduction, and processing. Sorry.
It's okay, Sugai.
Okay. So yeah. In this slide, we could see the software named Psychopharmacology. This is a user-friendly software to analyze data using the machine learning methods. So it's based on the Python and the computing language, but it's really user-friendly. In our team, we usually select this software to analyze data. Next. Thank you. Okay, we published a paper in this year. It's named Convergence and Divergence of Neurocognitive Patterns in Schizophrenia and Depression. Yeah, in this paper, we analyzed the neurocognitive data with machine learning methods. So it's a numeric data. So we are very glad you could download and cite this paper. Next, thank you. Okay, the main theme about the topic is about the neuroimaging study. So we have a paper under review in Schizophrenia Bulletin. It's the classification of first episode schizophrenia using multimodal brain features. It was combined structural and diffusion imaging. Next. Okay. So in this study, we had two data sets. The data set one included 98 patients with first episode schizophrenia. Sorry. Okay. No. Last no. Yeah, last one. Yeah. Okay. The previous one. Okay. So and 106 mass healthy controls. The participants in this data set were scanned using the Philips MI scanner. In the dataset 2, it included 54 patients and 48 mass healthy controls. In another scanner, is a GMI. Okay, next. Next, please. Okay, yeah. So we have two modules of the MI imaging data. So one is the structural MRI, is T1 weighted image. The T1 weighted image were processed using the free server. Using the Descalini atlas, the 68 cortical regions were defined as regions of interest. Then we acquired computed the cortical grammatic volume, cortical thickness, and folding for the 68 cortical regions. And then another module is DTI data. So we use the DTI data were processed using the FSL software, using the GHU DTI based on white matter atlas. The 48 fiber tracks were defined as RIs. So we then computed the fractional anisotropy and mean diffusivity for the 48 fiber tracks. Next, please. Next slide, please. Okay, so yeah. So we get a matrix. We got matrix is about the M subjects by M features. So in the single module, we like the N subjects by structural MI matrix, or the subjects number of subjects by the DTI matrix. So we then we could we also could like we also could combine these two modules to get the fused matrix. Okay, after obtaining the variables from each neuroimaging metric, the gene importance of each feature was computed to identify which neuroanatomical features contributed to the discriminative ability of the classifier. In this study, we used the gradient boosting decision tree. The GBDT is an improved boosting algorithm for regression and classification problems. This is an ensemble machine learning algorithm. Okay, so the gene importance, also named the mean decrease in impurity, calculates each feature importance as the sum of the number of splits, then include the feature proportionally to the number of samples it splits. So okay, so yeah. Then we applied the methods to the neuroimaging metric. So we had two data sets. In the first data set, we trained the classification model. In the second data set, we tested the classification model. So when we got the original data set, we pre-processed the neuroimaging data, then regress out the age and gender as covariance, then normalize the data with the z-score method. So then we use the tenfold cross-validation to select a feature, to train the model and select features. In this procedure, we shuffle the data for 100 times. So shuffling is a very good method to reduce the randomness of the results. So it means that we do the tenfold cross validation 100 times. So in each cross validation, we got the results. The highest we got the accuracy, the performance of the classification model. Then we also get the rank of the features importance. If the feature appeared more than 95 times in this 100 times. These features were defined as the most frequently selected features. Yeah, so we got the most so through this we got the most frequently selected features in each metric and the fused metrics. And then we use another tenfold cross-validation to in another dataset, in dataset 2, to test the classification model. Finally, we got the average predicted scores for each metric and the fused features. So, questions is open. So, okay, next slide, please. Yeah, so we could see two pictures. The left is for the performance of the accuracy of the dataset 1. For we could see for the for the great matter volume, thickness, gyrification, fractional anisotropy, mean diffusivity, and the four fused matrix. So we use the four fused matrix is thickness, gyrification, FAMD. Then we select features from these four fused matrix. So we got then we trained the model and test the model to get the accuracy. Five metrics. Yeah, it's about the GMA, thickness, gyrification, FA, and MD. So we also do the same analysis. So the left picture is for the accuracy in the data 1. The right one is for the right one is for the data 2. Like in this picture, in this slide, we could see that the FA have a higher FA and gyrification has higher accuracy than the other three metrics in the single metric level, and the full fused metrics had a higher accuracy than the single metric, and the features selected from the five fused metrics. So, but in the data 2, the accuracy of the based on the most frequently selected features of FA didn't get a higher accuracy, higher percentage. But the four fused features of the most frequently selected features from the four fused metrics also has a good accuracy, a good classification. Next, please. Sorry, next. So, based on the most frequently selected features from fused structure and DTI metrics, classification accuracy of 75.5% was achieved, which was higher than the accuracy derived from a single imaging metric. Okay, so the most prominent discriminative features included the cortical thickness of left transverse temporal gyrus and right para-hippocampal gyrus, and the fractional anisotropy of left cortical spinal tract and right external capsule. In the independent validation cohort, and the average accuracy was 76.54% derived from combined features selected from cortical thickness, gyrification, fractional anisotropy, and mean diffusivity. Next, please. Next slide, please. sorry, next slide, please. Okay, so this is a most frequently selected features from the single metric of FA and single metric of gerification, because these two metrics had higher accuracy in the training model. They said so. So we listed the selected feature, most frequently selected features from this these two single metrics. We could see there in this table we could see the selected feature and their feature importance in the classification model. So if the feature importance was higher, it means that the feature in the model had the higher discriminative power. So next slide, please. Okay, so in this table, we listed the most frequently selected features from the fields of metrics. Yeah, it include in the four fields of metrics included cortical thickness, gerification, and fractional anisotropy and mean diffusivity. So we also could see the feature importance for its selected feature. But in this table, we could see that the cortical spinal tract has the highest feature importance in the model. Then the transverse temporal cortex. Okay, next please. Okay, we also plotted the regions, the most frequently selected regions in the illustration. So we use the MAYAVI is a Python API. It's So we got a nice figure. Next, please. Next slide, please. Okay. Yeah. So in our study, our study achieved modest but robust classification accuracy by adopting the gradient boosting decision tree to the multimodal brain features. The classification performance based on the discriminating brain regions selected from the fused structural and the DTI metrics was relatively higher and more robust than performance based on the features selected from single imaging metrics. Next, please. Yeah. But one thing we would like to point out is why different studies with different classification performance. So we also discussed a lot in the paper, in the article. So considering like the differences in pipelines for imaging processing, feature selection, feature extraction, or dimensionality reduction, and the pattern recognition methods. All these differences could at least partly explain the above discrepancies across studies. Like another reason is a potential factor, like is a biological and clinical heterogeneity of schizophrenia. When we reviewed, when we raised the papers about the machine learning, we could find out that the homogeneous small samples usually achieve more encouraging accuracies but are prone to have a higher risk of overfitting. So yeah, in this paper, okay, okay, yeah. In this paper, we validate the classic model with another data set. So I think this is different from most of the previous studies. So yeah, thanks for your attention.
Sugai, thank you so much for your great presentation. We apologize for the technical difficulties again. Are there any questions from the
And
audience?
questions?
Please. Yeah.
Hi, Sugai. It's Andy. Thank you for such a very clear and good talk. I have one big picture question for you. They still on? Oh, it's disconnected. Sorry, they won't be able to answer my question. Oh no. Are you reconnecting? No. It's stuck. But can you hear us, Sugai? No. Yeah. Yeah.
There, on this side.
Yeah.
Just like their upload is faster than
Yeah, it'd be good if we could get one question, just for the speaker. Yeah. Well, she's there, so on our screen here. Even if it's just audio, would be good. Let's give a presentation as a junior person, and it disappears. Yeah, because of the technical difficulties, we will not be having the subsequent speakers, but we may have a question. Are you connected in, Sugai? Can you hear us? Hello? No voice? Okay, maybe we could just send them a message and let them know. And that's it. Okay, well, thank you very much for persevering. I think Mark and I both think this is the most technically challenging symposium we've run. So we'd like to thank the speakers, and particularly Shimin Li, who's here, for persevering with us. Thank you so much.
Thank you.
And now you're free till the 5 o'clock.